Hi, I'm Ed Artuni, a member of the Implosion and Stagnation Nuclear Group, which is a part of the Joint High Energy Density Science Organization working at the National Ignition Facility at the Lawrence Livermore National Laboratory. Thank you for viewing my poster, Interpolating Individual Line of Sight Neutron Spectrometer Measurements onto the Sky at NIF. Sorry we could not meet in person. Let me take you through my video poster instead. The central question of this research concerns diagnosing low-mode asymmetries of the implosion of a spherical, fuel-filled ablator capsule heated within a hohlraum. The hohlraum radiation field transfers energy to ablate the capsule and results in a radial force that compresses and heats the fuel. If the ablation forces are not radial and uniform, energy that would go into compression is lost into translational and rotational motion of the capsule and the fuel. This lost energy represents an inefficiency in the implosion process. Our understanding of the asymmetries can provide a way of controlling them and in the process provide more energy for compressing and heating the fuel. By low mode, we refer to perturbations in the shape of the burning plasma hotspot and fuel shell. The hotspot is a region of fuel that is generating neutrons as imaged with both X-ray and neutron diagnostics. The size scale of these low-mode shape perturbations are of order the radius of the hotspot. The first indication of strong low-mode asymmetries was the observation of hotspot velocity. The velocity is observed as a shift in the mean value of the neutron kinetic energy spectrum. There is an expected shift due to the ion kinetic energy distribution in the gamma window, 5 times the temperature of the plasma. The neutron time-of-flight diagnostics measures the time and space integrated kinetic energy spectrum. The observed velocity is a quantity of the average plasma motion. The kinetic energy distribution's second moment provides a measure of the ion thermal temperature, with a significant contribution from the variance of the ion velocity. The third observable is a downscatter ratio, DSR, the ratio of the neutron yield from 10 to 12 MeV to the yield from 13 to 15 MeV. This ratio measures the fraction of neutrons elastically scattered off the compressed fuel shell through an angle parallel to the detector line of sight direction. Spears et al. Pursued the hypothesis that laser drive asymmetry could cause a hotspot velocity in verified 2D hydro simulations with the shot N150318, for which the laser pulse was set to be top-bottom asymmetric by plus 4% to minus 4%. There are 3 predictions from the physical picture which are the subject of this poster. 1, the hotspot velocity indicates the direction of the perturbation. 2, that there's a T-ion asymmetry is a function of angle to the velocity direction that goes like cosine squared theta. And 3, there is a DSR asymmetry that goes like minus cosine theta. That is, low DSR in the direction of the velocity, high DSR opposite to the direction of the velocity. The perturbations in experiments can come at any angle. The magnitude and direction of the quantities can be represented on the surface of a sphere, the sky. The neutron spectrometers are located along 6 line-of-sight directions around the NIF target chamber. Each measures the hotspot velocity, T-ion, and DSR. We form the angular distribution of the hotspot velocity, Tion, and DSR for any angle in the sky by interpolating from the line-of-sight measurements. For velocity, we use a model that includes a 3-vector hotspot velocity and an isotropic velocity due to the temperature-dependent shift of the neutron mean energy, which is always positive. The Tion is taken to be a fit of an isotropic component and a cosine squared C component with respect to the axis of symmetry, which can be tipped at an angle of theta and phi. The DSR is fit to a spherical harmonic expansion to L = 1, which is essentially an isotropic component and a cosine C component with respect to an axis of symmetry tipped along a theta and phi angle. The hypothesis of Spheres et al. Would have all axes of symmetry aligned with the mode 1 perturbation. Shot 190918 from the recent high E ICF campaign will serve as an example. In the velocity sky map, the line of sight velocities are color-coded. NIF, MRS, and SpecPL did not participate. The mean direction is indicated by the star symbol. The point cloud indicates the velocity directions, where each line of sight velocity is varied by a random Gaussian distributions with the velocity mean direction and a 5 kilometers per second sigma consistent with the measurement uncertainty. The Tion sky is consistent with the cosine squared C distribution with the axis of symmetry indicated by the box symbol. The 1 sigma error bars on the direction are shown. The velocity direction is also indicated by the star symbol. The DSR distribution shows a maximum DSR at the diamond symbol. The antipodal point is indicated by the 1 sigma uncertainty contour, which includes the velocity direction and the Tion axis of symmetry. The red triangle is the result of an analysis of drive asymmetries. This drive asymmetry is a combination of laser imbalance, the effect of the diagnostic windows in the Hall realm, the non-uniformity of the ice layer thickness, and the non-uniformity of the ablator capsule thickness. The agreement of these 4 independent analyses are evidence that the mode 1 perturbation hypothesis from Spheres et al. Can explain the implosion data. Further, combining the individual line-of-sight measurements of the neutron spectrometers provides a sensitive diagnostic of low-mode asymmetries. Thank you for your attention. I'd be happy to answer any questions you might have.